Hello everyone, this is a workshop for styrene production, and what we would like to do is to produce styrene from ethyl benzenes. There are three reactions involved in the production of styrene, including the styrene decomposition to benzene and toluene. These two are undesirable reactions. By these three reactions here, the first reaction is reversible reaction. So we do have the rate expression for forward and backward reaction based on its element. By the reaction number 2 and number 3 here, it's quite forward to the right hand side. However, when you look at the EA activation energy is quite high, so the reaction not very favorable to this condition. One thing that we have to keep in mind is that styrene is quite spontaneously polymerized at high temperature. So what we do is we cannot have the temperature of styrene higher than 125 degrees Celsius, and of course the condition as you see in the workshop, the pressure will keep low in vacuum condition. Alright. By this handout, I would like to remind that the unit that used in particular rate expression here based on this, for example, EA activation energy has the unit in calorie per mole and temperature in Rankine, pressure or partial pressure here in kilopascal, and of course the reaction rate based on 1 mole per a mole per cubic meter and second. Well, later on, the reaction here is quite endothermic. So, what they try to push the reaction forward is to increase the temperature from 16 degrees Celsius of ethylene go to 800 by mixing with the high pressure stream. In this case, the high pressure stream that we using is a superheat stream, which will provide energy to drive the reaction, and the steam that we are using here is an inert, will not do any reaction to ethyl benzene in this particular condition. Okay, let's begin with the feed streams of ethyl benzene, and at 16 degrees Celsius, 20 kilopascal, and the input is 180 kilomole per hour. And we will learn how to input the information of rate expression in the HYSYS here. Well, starting with the fluid package. So we're going to use this SRK, and then we're going to input chemicals. we do have ethylbenzene. Now we add styrene on it. Hydrogen, that's for the first reaction. And then we do have benzene and ethylene, C2 double bond, and then toluene, and the last one is C1. Okay, that's all the chemical using in the reaction. However, we need to input water to the system as well as an inert. The system turned green now. However, we need to add the reaction in that. As you can see here, the reaction that can be used in the HYSYS refer to conversion equilibrium, heterogeneous catalytic reaction, and kinetics 1. Based on what we have here, there's only the expressions look like kinetics, so we prefer to using that. We are 3 reaction. Alright, now we start with the first one. So we use ethylbenzene to produce styrene and hydrogen with stoichiometrics -1 and 1 and 1. That's the product. Okay. Then we go to Then we now go to the the order for the forward is 1 to ethylbenzene, and backward is 1 with respect to other one respect to styrene and hydrogen, which is okay. And when we see the balance is 0, it's good. So the stoichiometric coefficient is alright. And the reaction is quite endothermic by 1.2 to the power of 5 kJ per kilomoles. Now we change that because the expression we have here is in terms of pressure. So we move that to partial pressure and using the overall reaction phase. The pressure we are using in kilopascal, which is right, and the rate that is the default in the software is in the unit of kilomole per cubic meter second. But what we have here in the handout is based on mole. So what we're gonna do is divide that the rate constant by 1000. Okay, so let's do with the first one. So the first one, A, pre-exponential this pre-exponential rate constant here should be 4.24 10 to the power of 2 after divided by 1000. But the EA, which is E here, what we're going to put is 21708, but this unit is in calorie per mole. So remind that we have to use the right unit here. So I input 4.42. Let's put this. Alright, and then the number is 21708. 21708. Change that to calorie per mole, and the software will convert to what the default unit here is, and that's convert to kilojoule per kilomole there. Okay, let's go to the backward reaction. So what we have is 0.755, and this is require a minus on the front. 7804. So I put 0.755 E minus 3, and then go to 7804. It should be minus here. Okay. Do you want to keep the negative value? Yes. Okay, that's alright for the first reaction. And the mark is say OK. Go to the second one. This case is decomposition of ethylbenzene. Go to benzene and ethylene by minus 1 and 1 and 1. But we don't have the reverse reaction. Make sure that this would be the same partial pressure and overall. So let's see what is the number are. So we have 7.21 E5 and 48675. 7.21 E5. Oops, I forgot. 48675. 48675. Okay, this reaction also in endothermics. Last reaction is hydrogenation of ethylbenzene to taurine and methane. So you have minus 1, minus 1, 1, 1. The reaction based on both of the reactant. So, but only in the forward reaction. So we do change that again. And the values are 1723, 26857, 26857, 1723. Okay, this reaction is negative. So the reaction is endothermics. Exothermic, sorry. Now, even the reaction is complete, but we do need to add it in the free package. Or what I mean is that we have to combine the reaction with the thermodynamics properties to compute the property and using in the system. So what we do is just click that. So we add that into SRK. And now this will go together as a set number 1. In case that we do have another set here, set number 2, they will can be used to add to another fruit package as well. Okay, now all here show no red sign, so we can go to the simulation and starting with the feed stream. In this feed stream, of course, we have the temperature at 16 degrees Celsius, 20 kilopascal, and the flow rate of 180. However, it's required the composition of that. So, as the pure feed, it's quite easy. Okay. According to the handout, I put that ethylbenzene feed is mixed with the recycled one, so we prepare for that. So I put the recycled one here, the recycle unit. I mean mixer here. Okay, this is nothing to do with the mixer because it's only one stream coming in. And then because this ethylbenzene will mix with the high pressure stream at 200 kilopascal, so what we have to do is to boost up this pressure to 200 kilopascal. So what I do, let's check. This is the liquid phase. Ethylbenzene is in liquid. So what we need is to add pump. This is to boost up the pressure to 200. We require some work here. And now it is ready to mix with steam. So I have number 3 and number, let's see, steam. Go out at number 4. Of course, we need to add some information of the steam here. So it's going to be very simple because only steam, superheated steam is coming in with the condition. Can you remember that? The temperature is 800 degrees Celsius with a flow rate of 8,000. So we have that 800, 200, 8,000. Well. Now what we do have here is temperatures come down to 691 degrees Celsius after the mixer, but the pressure is still same. Okay, we now can put that to the reactor. Okay. Before going to do that, let's check. Now the phase is in gas. it is a gas phase. So we probably not to use CSTR in this system. Let's check to the reactor. The reactor number 1, of course, we should have catalyst inside, so the void fraction is not totally 1. There has some catalyst inside, and the reactor is equipped with a 20 meter tall with a 3.6 meter of inner diameter, and there are 5 tubes. So let's see, how can I do that? I use rating here. So we have 20 meter diameter of 3.6, and there are 5 tubes inside. Okay, we do not need to add, and of course inside the reactor we can calculate the pressure drop inside the reactor, because we need to calculate the pressure drop since there is something as the catalyst particle obstruct the flow. So the pressure drop should be taking place here. So what we use is an eigen equation to calculate the pressure drop inside the tube that have something obstruct the flow. Okay, so we use number 5, and now to number 4 and number 5. We prefer to use because the reaction is endothermic. So we will use the heat that generated by the reaction. So we don't need to add any energy or remove them. And the reaction that using is set number 1, and what I mean is 3 reactions together in this set. Now when we put that, the simulations is completed. So let's see how well of the performance we can find that from the result. And as you can see here, the first reaction has the rate of the conversions about 21%, 23 and 17% base ethylene So it's nice. Oh, I have to go back because I forgot to put the void fraction 0.9. Okay, that will be a little bit off. Okay, this change, keeping a little bit lower. Okay, we do have to put another reactors here. It is probably the same. So I put the eigen equations to calculate the pressure drop, and then the length is smaller, shorter with the smaller diameter, but still have 5 tubes. And we do put some catalyst inside. See what I forget? I forget to add the reaction sets. Okay. Now I'll compare number 4 to number 6 based on ethylbenzene. By the ethylbenzene feed into the system is how many mole? 180. So what you get here, mole 67. So what is the overall reaction respected to ethylbenzene? So that probably from 180 to 67, about 45% of conversion-based ethylbenzene. The condition coming out here is in gaseous phase, and temperature still high, pressure is still 185. So what checked by the composition. You can see that there are a mixture of several things here. Because of the high pressure, high temperature, so everything are in gaseous phase. So what we can do is to reduce the temperature down, and also flashing by putting the reducing valve to reduce the pressure as well. So that will make that will separate hydrogen out from the system as well as liquid water. So from this chemical have 8 chemicals here. What we should do is to put 3-phase separators to separate it, but before that we need to release the temperature and pressure down. So what we use is to put the cooler. Number 7. And that number 7 will go to the 3-phase separator, the top one. Probably take the hydrogen out. Number 9 is only the medium hydrocarbon. Down here should be water. Okay. So what I'm doing here is try to decrease the temperature down to 65 and 100 kilopascal. Just want to this condition will do some separation here, from 1 to, and 2% of vapor. Okay, we do have to reduce the temperature and pressure from the outlet here. Let's check again. We do have the gaseous phase coming out from the reactor, and this temperature and pressure is quite high. So what we do is to reduce the temperature and pressure down, ready for the flash. And of course you need to check for this vapor fraction, that you have something not 0 or 1. So let I reduce that to 65 degrees Celsius and 100 kilopascal, and the fraction of vapor is about 2%. To do more separation here, by putting the reduced more 10 kilopascal here. Okay, now we can check the outlet from the 3-phase separator. Let's go to the one below. We expect to have only water. Of course, when you look at the mole fraction here, something should be mixed, but not very much. See, you can see a little bit because it's of the solubility, I think. And now go to the one in the middle, which is expect to have only ethylbenzene, styrene, benzene, and toluene. We also have something mixed, but not in the very big portion, so it will be okay. So these 4 of them will go to the separator. Okay, now let's see on the top one. We do expect to eliminate all hydrogen here, and some light gas, methane and ethylene, which is good. Make sure that you don't have a hydrogen amount much to the separator. Okay, now it's time to put the distillation here. Okay, back again to the styrene production, but before that, before the separation, we come to understand about the boiling point of each chemicals involved in the separator phase. We have benzene, toluene, ethylbenzene, and styrene. All of these, the boiling point of all these are 80, 110, 136, and 148 approximately. So in the first column, we start with using the shortcut. And connect with number 17 and number 20 here, 21, with the condenser of QC1 and QR. Before doing that, we should come to a specification of the column. And in column number 1, the toluene should not be in the bottom, higher than 0.1% by mole, and ethylbenzene should not be in the distillate higher than 10%. In this case, what I mean is the light key, which is toluene, should not be in the bottom higher than 0.1%, and heavy key should not be in the distillate higher than 10%. So come back here. So they get is toluene is 0.001, and then in this case is 10%. Okay, and the pressure at the reboiler is about what we input by the 10 kilopascal loss. So what we get is 80. Okay, with the reflux ratio of 2, so I use it 1.5 times, so I approximate to be 3. Enter. So then what I get from the first column is to separate benzene and toluene out. How about the bottom one? We do have a lot of benzene and styrene down here. So the next step is to use another shortcut to connect with number 22 and 23 and 24. Okay, with the condenser heat and reboiler heat. Okay. So in this case, of course, we are working on ethylbenzene and styrene here. And the specification is that ethylbenzene should not be in the bottom higher than this. So what I use here is ethylbenzene is lighter and heavier one is styrene. So I have that equal to 0.005 by heavier one should not be in the this ethylbenzene by 1%. So I put it that number. The pressure at here still 90 by loss of the pressure by 10. So I get is 80. Okay. This is about 9 to 10. 10 2 times. Let's see what happened. Oh, it's alright. So we now have ethylbenzene ready to the recycle. See, most of them is ethylbenzene compared to styrene is only 1 kilomole per hour. So now what we are doing is think about the pressure here is 80 kilopascal, while the pressure at this point equal to 210. So we need to increase the pressure. And of course at this stream all of them is in vapor phase. Liquid phase, sorry. So I can add the pump and then boost up to 210. However, I think I forgot to add the verb require. Pump to. Okay, now we do need a recycle because later we can have this ethylbenzene go to this recycle. Okay, recycle this one. So I make it 26 to 27, and then using the parameter of simultaneous, Now it is about the same pressure but different temperature. And Ali? We need that to connect with 27. Okay. So in this case, we cannot recycle all ethylbenzene to the system because of distillation column has been fixed by the performance. So what we need to do is to work on the flow ratio. So only 40% can go to the recycle route, but another 60% of the flow of ethylbenzene have to go to the storage. But of course, it will come to this part. Alright. That's all for the styrene production, but what you have to do is to work on the legless distillation here and change this symbol to be a legless one, as what we learned from the previous workshop. And of course, the composition that came out here and the flow rate might be different compared to before we have the recycle. That's all for today and have a nice day. Thank you.